Hello my people, hope we're doing well. This is the third video in this series that we're calling Evaluating Riemann Sums Numerically, or something similar to that. And in the first one, we basically just looked at it graphically and got a sort of a spatial and pictorial understanding of what's going on with these Riemann sums. In the second video, we added to that actually computing these Riemann sums, these area approximations, by means of just adding things up, okay? And we did that in that second video by means of right-hand Riemann sums, allowing the function value at the right-hand side of the subinterval to determine the height of the rectangle in that subinterval. As we move to this next video, we're going to be doing what are called left-hand Riemann sums. And if you're thinking, does that mean we're going to be using the function value on the left-hand side of each subinterval to determine the height of the rectangle in that subinterval? Yes, you would be absolutely right. But let's go ahead and work through that. Now again, we're using the same function. This is f of x is equal to 9x minus x cubed. Okay? And we are doing it from 0 to 3 with 6 subintervals. Okay, so just like the last time, we're basically chopping it up into these subintervals. Okay, but before we actually get too far, I want us to notice something. Okay, and that's this. If we compare how we compute the heights of those, if you'll notice, the height, this represents the height of the first subinterval for the left-hand Riemann sum in this interval. This represents the height of the second, but it's the same as the height of the first for the right-hand Riemann sum, and that's because what is left hand for the second interval is right hand for the first interval. So basically what that means is if you get a different value for your left hand and your right hand Riemann sum, it's not because of anything that happens in the middle, because for this rectangle right here in the second subinterval is going to be the same area as this rectangle in the first subinterval for the right hand Riemann sum. What you're going to get is the difference between the two is going to be what happens at the ends, okay? And in this case, you're going to find out that you actually get an identical one because basically both of the endpoints wind up being at a 0 for the function. So even though this rectangle for the right-hand Riemann sum is different from this rectangle of the left-hand Riemann sum, they are equivalent because they both have a height of 0. But let's not get too far ahead of ourselves. Let's go ahead. Okay. Now, like I've said before, the area of each rectangle will be the product of the uniform width, okay, being, in this case, 1/2, and the right-hand function value, or in this case, the left-hand function value. I guess I just failed to edit that. So let's left-hand function value. So the area approximation will look something like this. Okay, it's going to be the area is equal to, now again, area meaning the approximate area, the area of the accumulated, and you just have to be specific, especially if you're being asked to calculate one thing or another. It's all about just being notation, being clear in your notation. But this one, of course, will factor out the 1/2. And then, of course, we're going to use, since it's going to be the left-hand Riemann sum, we're going to start at the left-hand beginning of the interval instead of one subinterval inside of it. When we did the right-hand Riemann sum, we started at f of 1/2 and we ended at f of 3. For the left-hand Riemann sum, we're going to start at f of 0 and end at f of 5/2 or f of 2/2. Okay. Now, basically, once we've done that, and we get down to this, we get the area is going to be equal to 1/2, and we're going to have those big braces again because we're going to be evaluating we're going to be evaluating f of 0, which is going to be 9 times 0 times 0 cubed, plus f of 1/2, 9 times 1/2 minus 1/2 cubed. Okay, and then 9 times 1 minus 1 cubed, and then 9 times 3/2 minus 3/2 cubed. Close that with a bracket. 9 times 2, minus 2 cubed. And of course, last but not least, 9 times 5/2 minus 5/2 cubed, right? And if you actually flip back a couple of pages and look at this similar construction for the right-hand Riemann sum, the only one that's different is going to be this, right? You almost have this sort of like what is not included here, what is included on the other one. For the right-hand Riemann sum, you had a final term of 9 times 3 minus 3 cubed, right? But that right there, which has a value of 0, was replaced by this one here, which has a value of 0. So that, in terms of numerical equivalence, is why they're different. But notice that if you flip back to that page in the past, these values in here are all the same. Okay, they're all present in the right-hand Riemann sum, because this was simply the first value instead of the second. This was the second value instead of the third, and again and again and again. Okay, so as I've said before, in this scenario, it worked out that the same approximate area as the right-hand sum. Now, this is seldom the case. By the way, remember that it wound up being 19.688. Okay, it's seldom the case. It just so happens that the first left-hand function value was the same as the last right-hand function value. And then, of course, if you look back at the graph, you'll notice that it has x-intercepts at both ends of the interval. If the interval had been 0 to 2 or 1 to 3 instead, we would have gotten different approximations. Now, let's actually look at some different ones. And for the left-hand Riemann sums, we will actually be doing some problems that look remarkably similar to the right-hand Riemann sums, and some of them will be different, and I think that's instructive. This is another one of those ones that I pilfered from a book, but I want to change, so we're going to instead do this for 4 subintervals like we did it for the right-hand Riemann sum. Now remember that this function that we are asked to entertain here on this interval actually factors into x minus 1 squared. That might be helpful here before long. But let's go ahead and actually draw those rectangles that we're going to need. But remember that I need to subdivide 0 to 2 into 4 pieces, which means I need this right here at 1/2, and I need this right here at 1.5, 1.5, or what I usually like to use is 3/2. Now, this right here is going to be the function value on the left-hand side of this first subinterval. So that is going to determine the height, right? That function value is going to determine the height. This right here is the left-hand function value for the second interval, spanning from 1/2 to 1, and therefore it determines the height of this rectangle. This right here, f of 1, is going to be the height to determine this next subinterval, and you're thinking, that looks like 0, and you'd be right, it is. So that third subinterval has a rectangle of height 0, and then of course this fourth one has a height at f of 3/2, and actually because of symmetry, these two smaller rectangles are exactly the same size. Okay, we saw something similar with the right-hand Riemann sum, but let's go ahead and actually do the work. So we have the area is equal to 1/2 f of 0 plus f of 1/2 plus f of 1 plus f of 3 halves. And this winds up being 1 half. Well, f of 0, you plug that in, you get negative 1 squared, and that's going to be 1. You plug in 1 half. 1 half minus 1 is negative 1 half. Negative 1 half squared is 1/4. And you plug in 1, you're going to get 1 minus 1, or 0. 0 squared is 0. And then 3 halves minus 1 is 1 half. 1 half squared is 1/4. And you might even remember those values because they were actually the same values from the right-hand Riemann sum of 4 subintervals from 0 to 2 of the same function. They were just in reverse order, okay? So we should expect that this is another one of those ones that's actually going to have an equivalent area from the left-hand Riemann sum to the right-hand Riemann sum. And of course, it actually rarely happens. It just so happens the ones that I've chosen, especially these beginning ones that are easy in arithmetic for the sake of being training wheel questions, I've chosen them on purpose to be simple, okay? So that we're not distracted by insane arithmetic. We can actually focus on exactly what we're trying to do in terms of understanding Riemann sums, their mechanics, and their conceptual undergirding, okay? Now, let's move on to one that is a little bit more difficult, or at least different from ones that we've seen in the past. And of course, if you're thinking, we've seen that graph before. Yes, it's the Witch of Agnesi. I love to use it and the related function, the Serpentine function, just because of the symmetry. And so basically what we have here is we want to evaluate the left-hand Riemann sum area approximation for this function for subintervals on the interval from -2 to 2. Right? And so basically we are going to have, unlike the ones before where we had oftentimes a width of 1 half, this interval is 4 units wide. It needs to be subdivided into 4 subintervals, so each one of the subintervals is going to be exactly 1 unit wide. So we don't have a fraction. We just have the sum of all of the function values that are determining the height of each individual subinterval. So let's go ahead. And you're thinking, oh my gosh, this is going to be really cruel. It's actually not that bad. The values don't wind up being nearly that bad. If we, of course, we chopped it up into 16 subintervals, it would be a little bit more burdensome. But it is only 4 subintervals, and we are actually plugging in integers into the function in order to get these outputs. So they're going to be pretty simple fractions. So we know that our area is going to have each one of these areas has a common width of 1, and then this first one right here is going to be determined, its height is going to be determined by f of -2. And this second one is going to be determined by the left-hand function value, f of -1. And this third subinterval is going to be determined by the left-hand function value, f of 0, and last but not least, f of 1 determines the height of that 4th subinterval. And you can even, you don't need a calculator, you can plug it in. -2 gets plugged into here, gets squared, that denominator turns into 5, and you get 1/5. -1 gets plugged into here, -1 squared becomes 1, that denominator becomes 2, and you have 1/2. 0 gets plugged in here, and you get 1/1, or 1. And you plug in 1, because it's an even function, you should expect it to have the same output as it does here, and it's true. You would get, again, 1/2. Now, obviously, this right here is equal to 2. 2 and 1/5, or basically 11/5, right? And so basically you have 2 and 1/5, 2.2, or 11/5 is your area approximation. So let's go ahead and move on to one that is a little more difficult. This is going to be one that we're going to have to use the calculator for because, yes, we are going to be having irrational function values determining the height because we're dealing with a radical function. So it's about time that we kind of moved on from the training wheel stuff. But the training wheel stuff is there because, for a little while we need training wheels. Now, we have the function f of x is equal to the square root of 2 minus x. So that represents a horizontal shift and a y-axis reflection. which is why the function is now going that way, right? And it's going to be a left-hand Riemann sum on the interval from 0 to 2. And I provided the graph and cropped it and scaled it so that it's really easy to see. This function value right here, and let's go ahead and remind ourselves that that's going to be 1/2, and that's going to be 3/2, okay? So this height right here is going to go over to here, okay? Then this height right here is going to determine the second subinterval. And then this function value, or this height right here, is going to determine the height of the third subinterval. And then this function value right here is going to determine the height of the fourth subinterval. Now all we have to do is actually, write it out analytically and start plugging in numbers to determine exactly what it is that we have as an area approximation. Now notice that this is a left-hand Riemann sum, and the function is decreasing over the entire interval. Now that being the case, notice that that makes this necessarily an overestimate in terms of being an area approximation. So my area, notice that all of those subintervals have a 1/2, so I'm going to GCF that bad boy and just pull it out like I've done on previous examples. And then the height of each of those four, the first one is determined by f of 0, the second one is determined by f of 1/2, the third one is determined by f of 1, and the last one is determined by f of 3/2, which, you can represent these pretty easily. If you plug in 0 into here, you get 2 minus 0, so you get the square root of 2. If you plug in 1/2, you get 2 minus 1/2 in the radicand, and you get the square root of 3/2. Plug in 1, you get 2 minus 1, you get the square root of 1, which is, of course, 1. And then you plug in 3/2. 2 minus 3/2 is 1/2, so you have the square root of 1/2. Now, you could rationalize denominators, move them all together, work them around, but I will go ahead and spoil the surprise. This winds up being 2.173, and that is your area approximation. Now, is that reasonable? And the answer is yes. If you just look at the geometry of this, you can determine whether that's reasonable or not just by, if you were to, draw a straight line through here all the way and create this rectangle right here. That rectangle has an area of 2, right? Now, even that rectangle is going to be basically that rectangle is going to be an overestimate. And what you see here is the fact that your calculation is within that realm because you have a little bit over that rectangle and a little bit under that rectangle, and that kind of, all fudges in order to be roughly 2. So there are ways that you can sort of, ensure just by doing simple geometric arithmetic to determine whether you've made a keystroke error or you've made a calculation error or you've just done some mental math error or whatever, okay? And it's always a good idea to be asking yourself those questions in an ongoing way about each of the problems as you get to the end. Is my answer here reasonable? Okay, that brings us to the end of our third video, this one being, of course, on left-hand Riemann sums. The fourth and final video for this little series of videos is going to be on midpoint sums, and I will see you there.